Good evening, everybody. I'm Seth Shostak, senior astronomer here at the SETI Institute in the San Francisco South Bay area. And tonight we're going to bring you a slam bam, really exciting talk by two people who are doing some very interesting work that will greatly increase the number of targets that are checked out for SETI signals. Now, the SETI Institute, for the three of you who still don't know, the SETI Institute is a nonprofit research organization located, as they say, south of San Francisco, about 1 hour's drive. And we've been here for quite a while. That all has to do with an earlier affiliation with NASA, but you don't need to hear any of that. Our scientists tonight are from one from the Bay Area and another from, well, I'm not sure where the other one is from. And she's smiling, but she says it's top secret. I can't tell you anything about it. All I'm going to say here, in addition to all this, is that this is something that the SETI Institute does. We're a nonprofit. We run on the basis of your interest and your financial contributions. So if you enjoy SETI talks and you'd like to help us bring you more of them, please go to the SETI Institute webpage and you'll find all the obvious links to a place where you can help us out financially. Really appreciate that. All right, enough of that. I'm going to turn this over to your immediate host, Molly Bentley, who's, as it turns out, also co-host with me on our radio show, Big Picture Science. Molly Bentley, take it away.
Thanks, Seth. Okay, I'm going to introduce our guest tonight. Shanoa Tremblay is an astrochemist and radio astronomer who joined the SETI Institute in 2022. Although she's never been to Mountain View, California, the mountains are her home. She grew up in the White Mountains of New Hampshire, and the Sandia Mountains line her horizon in Albuquerque, where she lives and works on COSMIC for the Very Large Array, which is, as we'll hear, designed to expand the search for extraterrestrial intelligence. Dr. Tremblay says that the VLA, as it's known, is 2.5-hour drive from her home, or what we here in the San Francisco Bay Area call a short commute. The difference is she covers 125 miles in that time and we about 15. She brings to the hunt for ET her experience in Australia, teaching young students to find the closest thing that we have to aliens on Earth. Tardigrades are microscopic animals. They're extremely hardy. They can live anywhere. And she would tell her students as they trudge through the swampy water, even if you can't see them, from everything we understand about them, you have to believe they're there. So keep looking, we'll find them. Sound familiar? Welcome, chemist, astronomer, and tardigrade wrangler, Shanoa Tremblay.
Thank you. Good evening.
Good evening. Mark Rosendana is a postdoctoral student at UC Berkeley, living in Salt Lake City, doing research for the SETI Institute. He develops and implements software and signal processing techniques for these many projects: the National Radio Dynamic Zone Project at the Hat Creek Radio Observatory, the Breakthrough Listen User-Supplied Equipment Project at Meerkat, and the one he's here to talk to us about tonight, COSMIC SETI. Dr. Rosendana is, by his own admission, a computer nerd, but he wasn't always, even though he excelled at math and was a fan of comic books. He says that his first software programming class intimidated him. Years later, though, a signal processing project of a colleague caught his attention and he was hooked. Signal processing is a kind of a puzzle, he says. It is problem solving. When he's not at a computer, Mark enjoys rock climbing. He says climbing is problem solving on the wall. You have to figure out how to get up, and the answer isn't always just be strong. He's here tonight to answer questions about COSMIC SETI. Welcome, Mark Rosendana.
Thank you, Molly.
You're very nice to have you both here. Okay, let's kick this off. Shanoa, I know that you have prepared a quick and succinct introduction to COSMIC SETI, and you're going to share that with us with a few slides, so take it away.
Sure. So COSMIC stands for, it's an acronym. Astronomers love acronyms. And so it stands for the Commensal Open Source Multimode Interferometric Cluster, which is really a lot of words to explain it. COSMIC is a big computer. And this is what COSMIC looks like. This is what it looks like currently, right now. I took this picture last week, and it's a bunch of different equipment built together as one big computer system. We have a big team that works on COSMIC, and you can see also that includes Mark and myself. The COSMIC system is hooked into the Very Large Array, or the Karl Jansky Very Large Array, which is in this Y shape in the plains of St. Augustine in the western part of New Mexico. And this iconic telescope is most notable from the movie Contact in the book. Each of these 27 dishes are 82 feet in diameter, and we take each of the 27 dishes, a signal of them, and we process them to be able to do this real-time search for extraterrestrial intelligence. And so my role in this COSMIC team is that I actually work on site on a number, every couple of weeks, and plugging this equipment in, and then Mark itself is going to make it actually work. Thank you.
Okay. All right, Mark, your overview of what you do with this project, COSMIC SETI.
Yeah, so I essentially help with software development, among other engineers and scientists that are working on it as well. And I essentially help process the data from the telescope. And yeah, I think that's a succinct way of describing it.
Well, let's get some of the main points here, because computers, Shanoa, ran the VLA before this edition. So what is it about the COSMIC computers that actually improves the search for aliens? I mean, how would you characterize this improvement? What kind of leap forward is this?
So I think in general, one of the things that we get to do is we're taking a copy of the signal. So everything that the VLA has been able to do historically and currently, it can still continue to do. What we're doing is we're taking a copy of those signals. So at the same time that people are enjoying their normal science, we're able to take a piece of those signals and process them in real time. And this is an improvement compared to most previous SETI, where we had to go and use time on a telescope. So we had to be very careful about which targets we wanted to use or how we wanted to conduct the search, because we had a very limited amount of time. But now having something where we have a copy, we kind of do commensally, we do whatever the other astronomers are looking at, or what frequency they might be looking at, and we're able to process it in real time to do SETI. So it allows us to do it SETI at a much faster pace.
So it sounds like you're taking this group of radio telescopes. I believe there are 28, 27 that are always active. They always save one and work on it, I think. But 27 that are active, that have long been used as a tool for SETI research. But then what COSMIC does is bring new massive digital processing system that can collect more data, that can store more data. And as Mark said, also process more data, which is really important if you're looking for that signal from an alien. Can you give us a sense though? So I'll put it this way. It's my understanding that when this is up and running in the near future, it will observe 40 million galactic star systems, give or take. And I understand that will make it the largest SETI search to date, which is quite notable. Can you just give us an overview of what that means, the largest SETI search to date?
Yeah, I'm going to take this one, Mark.
Correct me, Mark, take it away. Mark, take it away.
I mean, Shanoa can speak a little bit more to it, but at least for me, so we'll talk a little bit more about it later on in the talk, but like with signal processing techniques such as beamforming, you're able to observe or to survey the sky at a rate significantly faster than with a regular interferometer or a regular telescope that's not utilizing the technique of beamforming. And yeah, so that's essentially how we'll be able to observe as many stars as you mentioned. So.
Well, and that number I mentioned, 40 million galactic star systems, is that a magnitude greater than we've been able to do in the past? Just to give us a
Yes.
sense of how much bigger this search will be.
So I think most of the previous searches historically, whether it's Project Phoenix from the 1990s or some more recent stuff, have been in the order of 1,000 to 1,500 stars. And those are programs that often have run for about 5 years. And that's the amount of data that they had been able to process in that time. And sometimes that's across multiple different telescopes as well. So we'll be able to do roughly the size of those 5-year surveys every single day or every 2 days.
Okay.
And this is a combination of the work that Mark's been doing and being able to observe multiple different objects at the same time, but also our system is hooked up at the same time that the VLA All Sky survey is going on. So they're actually observing every part of the sky that the telescope can see through a 2 6-month cadences. And when they do that, that means we get to see every piece of the sky to do a SETI search.
We're going to talk about the signals and what sort of alien signals you think that the cosmic SETI might be able to detect. And Mark just mentioned beamforming. That went by kind of fast. We're going to talk more about that in just a second. I do want to remind people that you can join this conversation by typing your questions in there where it says questions at the bottom of your screen, and we'll get to those in about a half an hour or so. What you just said about so the VLA does its regular, I think you said the normal listening that it does, or collecting data. I wonder if the C in cosmic is important here, because the C stands for commensal. Now in biology, that's a form of symbiosis in which one organism derives a benefit while in a relationship while the other one is unaffected. So it sounds like it sounds like is happening here is you're able to do the SETI search, but not disrupt. Is that right? The normal. I'm just laughing at that term. The normal, but the maybe some of the standard VLA experiments that are going on.
That's exactly it, and that's why it actually becomes kind of an efficiency, because people are proposing for time. They are doing their favorite science, whether they're looking at stars or black holes or whatever it is that they're looking at. And at the same time, we get to do our science at the same time. We get to be looking for these ETI signals. And so there's a huge efficiency gain from doing that. And so commensal is really important. It is this symbiosis. And so that challenges us at the same time, because what we needed to do was then design a system that it didn't matter what frequency we were looking at or what wavelength we were looking at, which part of the sky we were looking at, and still be able to use that data and that information to process it in real time to look for SETI.
As a fan of efficiency, I applaud you. So Mark, we're going to hear more about exactly how you sift through these signals. But first, let's discuss the signals that we're all hoping to detect. And sure, these are signals from aliens. Now, the Very Large Array, as Seth mentioned, or it was Shanoa mentioned, was made famous in the iconic image of Jodie Foster sitting near it with the headphones on in the movie Contact. In what way is the cosmic VLA search like that image listening with the VLA? And in what ways is it not like that? And this gives you a chance to just do some basic definitions for us, I think, about radio telescopes and even, go ahead.
Yeah, sure.
Yeah. Sorry.
So, I mean, yeah. So I guess the first thing is you wouldn't necessarily be listening to the signals. It's more of they're essentially images that would be generated, or data that's sifted through that we would search for what we would assume a technosignal or technosignature would look like. That technosignature, at least as of right now, the assumptions that we're going by are it would be narrow band. It would be significantly more. The bandwidth of the signal would be significantly smaller than what exists naturally in space. So So yeah, so essentially we'd be looking for a structure like that. And
It's going to be more sensitive. It has to be more sensitive to pick up the very, very narrow bandwidth.
yes.
That's one way. And an important thing is you're not listening for it, but in the way that it's similar, it is at the VLA, and the VLA just collecting the raw data.
Yes.
And that way it's similar. Okay.
Yes. So yeah, so then we would essentially be looking for that narrowband signal, and with cosmic specifically, with the beamforming that we'll talk about, I guess in a little bit, we're capable of essentially looking at multiple spots in the sky within the field of view at the same time, and look for that signal at essentially at the same time.
Let me just do a follow-up on that. I know you're excited to talk about beamforming. He's dropped it twice now. It's coming up later in the show, beamforming. Is that, okay, so you're looking for an aberrant signal, as you said, and but you're not going to hear it. Shanoa, is it going to pop up on your computer as like a, as a, a spike? Is it something you see, or is it really something you have to interpret? It's not something that's immediately visible as an aberrant signal.
That's exactly it, is we have to interpret it. So it's really just a change in signal, electronic signal. And so it would be like your lights flickering suddenly. But we have to take that change in the electronics and be able to interpret that to something that we can visualize. And so we do that through some different sets of software, and then we can make pretty plots of those electronic signals, and how they change as a function of either time or frequency or wavelength, if you prefer. And so by looking at those, what we're looking for is these little teeny tiny spikes that in frequency that are hopefully continuous in time, right? Because that would be really helpful. And you want to visualize that. But one of the things we have to also take into account is that the Earth is moving, right? We're moving and we're rotating. We're moving around the sun, and our entire solar system's moving in the galaxy. So we have to account for those things. And so that's going to change the acceleration of the signal depending on where it's coming from. And this is what we call a drifting signal. And so we have to take into account that drift as well. So we're actually looking for something that does have a drift, because if it doesn't, that means it's sitting on Earth. And so that's one way that we can kind of filter our own selves out in comparison to something that might be coming from outside of the solar system. That's a very important concept. And we're also going to talk about that, about how you determine if it's an aberrant signal, or is it a phenomenon that you're familiar with, and you have to be able to do a process of elimination to make sure it's not something that you're already familiar with. Mark, do you think it's important to just give a very quick, really brief distinction between optical astronomy? And I just say this because people are familiar with optical astronomy. Many people have put their eye before, a lens, and radio astronomy. Just in short, what is the difference? That I'm thinking of this because Shanoa said it's like if your light flickered, right? You think that's aberrant, but of course we're not working with light at all. I know she was just using that as an analogy. Mark, in short, what's the difference between optical and radio astronomy?
So in short, essentially in optical astronomy, you're using an optical telescope that uses lenses and so on to detect light, essentially. And with radio astronomy, we're using antennas. So it could be, in our case, we're using these very large antennas that have reflector dishes and a little antenna at the feed. And it's essentially just a difference in frequency. So yeah,
that's good.
I think that's one of the key important differences, that change in wavelength is a huge difference, right? Radio waves are millimeters to centimeters to meters, right?
There's a whole spectrum.
There's a whole spectrum. And so the dishes are designed to specifically be able to pick up those signals. And the optical telescope is sensitive to the same size, nanometer size light that our eyes are sensitive to, about 400 to 700 nanometers. And so the other important things for SETI as well from these different perspectives is that we have an ionosphere, a troposphere, an atmosphere around the Earth. And that can impact the different wavelengths in different ways. And so we have to take into account some of that as well. So like optical telescopes can't see through dust, for example, whereas radio telescopes can see through dust. So those are some important aspects as well.
What could we imagine an alien civilization is doing to produce, if it exists, and we believe that it exists, what could it be doing to produce some of these signals? I mean, when you imagine an advanced civilization, at the very least, what would they have to be able to do to produce any kind of signal? And then do you get more specific, like they have televisions, they have whatever it might be, they have machines, they are, I don't know, they have any kind of advanced technology or signaling technology. Does this, what do you imagine them doing, or what would they at least have to have created to produce these signals?
Well, I believe they would have technology at least similar to ours, at the very least similar to ours. Yeah, and essentially the big difference, at least as far as I understand, is that drift that Shanoa was talking about earlier. So the drift, along with the signal being narrowband, would indicate to us that it's from extraterrestrial life, as far as I.
Can you say more than when you said? I came up with a terrible list there. I was like TV, cars. I couldn't think. But Shanoa, can you give us an example of what kind of technology they might have? Because no, I won't do a follow-up yet. Just what are we imagining that would give off a signal that would travel that far?
Just in general, they're communicating, right? Is that they have some way of communicating, and we know that radio waves, we've used them for a couple different reasons. One, the electronics to either produce or receive radio waves tend to be relatively inexpensive to produce, for us at least. But the other thing is that they can travel very large distances. They're not impacted by walls, by doors. Our Wi-Fi works because, it's not blocked by the door next door. So that's kind of an important aspect. And I think one of the things that we're looking for is that constant communication that they may be doing. And so that's why we kind of look at radio with cosmic, but also there are aspects of looking at optical SETI as well.
So it's what you're saying is what they're doing is purposeful. They are actually trying to contact us, which helps. It's not just that their world has just the way that our television shows kind of go off into space. Those broadcasts go off into space. It's not incidental. It's purposeful. I didn't realize that.
Well, I think it's a combination of both. We're actually getting to the point where we're sensitive enough to be able to start eavesdropping, if you want to say, on another civilization. And maybe that's not the most polite thing to do, but that's essentially one of the things where our goal is to be able to see, are they sending a Voyager-like satellite away from themselves and still trying to communicate to that satellite, right? And so that's why we're not always so directed towards a particular planet or a particular star, is because they might be shooting these satellites out in various different directions and communicating, and maybe we'll pick that up.
We're trying to find each other. We're not just trying to find them, we're trying to find each other. Now, Mark, you work on the software side of things. And I want to just touch on this idea of processing, as you mentioned. So you have these raw data coming in to more than 24 antennas. Your job is to help process them. And why do they need to be processed? Why do they need to be processed before we can interpret them?
So actually it is just to enable us to interpret it or to help interpret the data as in a way that we can understand, essentially.
Okay.
So
otherwise it's just raw. It's just raw signals. Yeah,
exactly. So there are multiple ways that you could process the data and analyze the data. And so essentially you could, for example, look at the data over time, or you could look at the data over frequency. So I guess those are like the two most basic examples that I can give.
And time is important because, as Shanoa said, if it's repeating, or if it stays there, if it stays steady, that's important to know, right?
Yeah.
And then what the frequency is.
And I
Yeah,
guess
go ahead.
another thing also would be that the power of the signal itself would be very, very weak as well, just because it's significantly far away, or it's assumed to be significantly far away.
Yeah. So part of processing is boosting it, or is that what you mean? Or what do you mean?
So it's not necessarily, it is boosting it in a way. It's more just like there is a sort of like noise floor, and essentially you need to be able to see or to observe, to detect the signal that may or may not be below the noise floor. It mostly is below the noise floor.
Now, are all of these signals that we're talking about, I mean, the signals that are coming from aliens, let me put it this way, what you're hoping to detect are technosignatures, and I think Shanoa had mentioned that, technosignatures, it went by kind of fast. And these is a radio signal by itself a technosignature? And can you just give us a definition of, or just give us other examples of what technosignatures are, and maybe also a definition of what it is?
Yeah, so I mean, so a radio signal wouldn't necessarily just be a technosignature. We detect radio signals or radio waves from stars and so on and so forth.
So natural phenomena.
Yeah, so but the radio signal itself from an alien civilization would, or at least what we would assume the signal would look like, would be more narrow band, like I was talking about earlier. Yeah, so the narrow band structure, along with that drift that Shanoa mentioned earlier as well.
I think the general definition of technosignature is assumed that it's not created by us, anybody that lives on Earth, whether it's one of our satellite probes or a rover on Mars or anything like that. I think the technosignature name is usually applied for what we're looking for from another civilization. But
emphasis on techno, not bio. You're not looking for carbon. You're not looking for, right?
Right, exactly. You're looking for a technological sign that this civilization exists. And so this is often this, somewhat time possibly varying signal, because also their planet is going to be rotating around and various things. So they might go behind their sun, various things. And then also this frequency drifting signal. So we're looking for something of those two natures, and that's what we typically call a technosignature. So if we want a way to kind of think about this, visualize this compared to the rest of the universe, right? How do we separate these signals from everything else? And what we're looking for is these electronic signals. They're generated by light, but we can think of this to understand it by thinking about it from a sound perspective. So if we think about that, most of the universe has these broader signals, and so they're kind of like larger tones of, say, an organ, a church organ, or something that you might have seen at a big concert. Versus if you have a toddler with a toy piano that kind of goes tink, tink, and that's that technosignature. So that's that different sound that or that different way of the light being produced that's going to be different from everything else in our natural surroundings, and that's what we're looking for.
And you said you have to rule out natural phenomena. What sort of natural phenomena do you have to rule out?
So we know that stars are producing light, molecules produce light in a very narrow frequency sort of way, but still their signals tend to be broader than what we're looking for from an artificial sense.
So Mark, so you pick up a signal, let's say you decide that it's a natural signal, and then you have to go through and say, okay, is this a pulsar? Is this that you just have to kind of go through the list of things it could be? Is that right?
Yeah, a pulsar, or more than likely, it's just interference from us. Is usually the case. So
yeah, isn't the joke like it could be the astronomer warming up a burrito in the kitchen?
Yep. I think that
really?
Yeah,
is that actually a thing?
Yes. Yeah, so there was a long time where we thought that we had discovered some kind of new particle, and it was only being ever detected by this one telescope. And everybody else was trying to figure this out. Well, at some point, someone realized that it always coincided when we could do real-time processing, that it coincided by somebody opening the microwave door while it was still running. Not waiting until it beeped first. And then that released enough energy that the telescope could detect it. So now you'll see that either microwaves have been removed from the telescope sites, or they're put into special little shielded boxes so you can't open them while they're running.
Or people can start bringing cold lunches.
Yes.
Maybe perhaps that. One other just question on the technosignature, Mark, if the technosignature, can a technosignature be something like what Earth unfortunately produces as a byproduct of its technology, like pollution? Would like a fluorocarbon be a technosignature? Or is that considered kind of biological signature?
I think that would be a biological signature. I think the technosignatures that we're looking for would be more so like a satellite, for example, that like is communicating something. So yeah.
Okay. Yeah, in SETI, we tend to separate between biosignatures and technosignatures. Biosignatures means that a civilization could be emerging. It could be the very first signs of life. It might not have developed any technology to communicate or create electronic signals, or it could. It doesn't have to, though. Whereas the technosignatures, you require to have this certain amount of technological capabilities to be able to either communicate or produce some kind of electronic signal, whether it's optical or radio, doesn't really matter. But you're doing something, or you're so advanced that you're building megastructures around your sun, and then we can look for those as well. But in that case, you don't have to have a biological being that's creating those. You could have a entire planet of robots building electronics, and we could detect those through technosignatures. So they do tend to coincide with one of each other, but they are different approaches.
Fantastic. I just want to remind people to ask questions. You can do it by asking your question there in the Q&A. Mark, I do have a question for you, but it sounds like you were about to say something.
No, I was just thinking something. So I mentioned robots. I was like, well, Transformers might be.
Cybertron is on
That's for a breakout session. We're going to settle that. We're going to settle that later. Okay, so it sounds like we have three tasks here. You have collecting the data. I'm just repeating this because it's important to visualize this. So you're collecting the data in the VLA. You're storing the data, and then you have to process it, as Mark said, so it can be analyzed. One form of that processing, this is your moment, Mark, is called beamforming. Beamforming. What is that, and why is it important?
So it's the ability for an array of antennas to form multiple simultaneous beams, and I'll describe what those are, but to form multiple simultaneous beams on the sky, or in our case on the sky, within the field of view of the array. So the beam itself is more of a way to focus on a specific spot in the sky, if that makes sense. So without the technique of beamforming, it's essentially just a sort of like just orthogonal beam to the array itself that's focused on a specific spot within the field of view of the array. But with the technique of beamforming, you can form multiple of those at different spots wherever it is that you want to.
And is this because that signals tend to want to kind of just like a broadcast antenna, they just tend to want to scatter, and you kind of want to bring them into alignment like a beam? Is it a way of like directing and concentrating signals so that they're stronger or easier to read? Interpret.
Yeah, it's sort of a way of capturing the signal at whatever angle it's being transmitted at. So the way that it works, and the way, at least so far, the only way that it's known to work is you have to have multiple antennas. You have to have at least more than one antenna. So essentially, the way that you determine the direction of the signal is only if it hits one antenna and then hits another antenna at a different time. So that delay between the two antennas is what enables you to know that it's from a particular direction, if that makes sense. So then you would know that it's from a particular direction, and you can digitally focus on a specific spot within that field of view. And you can do that at different spots within the field of view. If that, yeah.
And then if you have those beams, do we call them beams?
Yes.
Okay,
Yeah.
beams. If one of your beams had captured an alien signal, you wouldn't know it until the scientists had analyzed it and came back and said to you, hey, Mark, beam number 2730 might have been, like this.
Technically,
so you wouldn't be able to tell from the beam that you'd then have to send it to the scientist to analyze it, and there might be a signal caught in that.
Yes, exactly. So essentially the data gets processed and stored in some files or something, or it gets stored in some files, and some other scientists would analyze the data and detect that signal. Or right now there is work being done on sort of machine learning algorithms to be able to detect the signal faster, or hopefully without the scientist having to like sift through data.
You're going to turn this. You're going to turn this all over to AI one day.
Yeah.
Well, I think, but Cosmic's a little bit more advanced than that, right? Because we actually don't have view the sky and then go to the scientists for analysts. We actually have a real-time pipeline that is actually finding these signals and putting them into a database, taking a piece of that data that said that the finder, let's call it, has said, oh, there's something interesting here. I'm going to cut a little piece of that data and we're going to save it over here. So then when somebody else goes and says, you know what, that one actually is really interesting, and let me go investigate it further, I can pull that data out. But that finder, that software pipeline has already run. And so I don't have to sit there and analyze the signals as they're coming off from the telescope anymore, which is really exciting.
Well, but you said it happens in real time. Do you really mean that? Like how much time passes between when you collect the data, you process it and you analyze it? How much time from the moment maybe you found that alien signal before you get the knock on the door and says, hey, we have something interesting here. If you guys have doors there, I don't know, but how much
Mark,
how much time?
I think you can correct me if I'm wrong, but I think it's somewhere along the line of 20-25 minutes from the time that we've recorded the signals to the point where it's in a database and it's been stored onto the storage drives.
That's exciting. Yeah.
And then I can go every couple of days and download the database and sift through it and go, well, this one's unique. This one's different than everything else. Why is it different? Okay, so let's say you find that, let's take the next step. Let's say you find an unnatural signal. You've ruled out burritos and pulsars and all these other sounds, interference, and you find one that's not natural. You haven't detected it before. Now, what's the next thing you do? You don't rush to the media and say, look, this is what we found. What do you do? What do you do next? No, so we've actually put in proposals on a set of telescopes around the world to be able to say, hey, we think we found something interesting. Let's see if we can see it again. And so not only just the VLA, which we can also then say, steer back around to here, we're going to try this again. But the Very Large Baseline Array, which is a set of 10 antennas that span across the United States. We have the Park 64-meter dish in Australia. We have the Allen Telescope Array in California in the Hat Creek Observatory, and we have the Green Bank 100-meter dish in Virginia. And so we can, call up all of these telescopes and say, hey, let's see if you guys see it. This is where it was. This is what frequency it emitted. Here's some of the properties. Let's go see if anybody else can find it. And so we're hoping that somebody else see it. If they don't, then it's really hard to say much about anything. You could try to go back and look every so often if you're lucky. But otherwise you kind of go, okay, we don't know. It can be the wow signal and everybody else can spend the next 30 years looking for it or so. Okay, so you bring up the wow signal. That was Ohio State University, I think, 1977. Maybe we should just say a couple words about that. Scientists, at least one scientist in particular, but scientists got very excited about that signal. It seemed like to fit all the criteria, checked off all those criteria up to a point. Can you just give us an overview, Shanoa, of the wow signal? What happened?
very briefly, and how long it took for them to realize that it was unfortunately not an alien signal.
So the WOW signal was detected by a telescope
And I should
called
say
the
it was
Big
wow.
Eared.
Yeah, wow,
Yeah.
because he said wow. It doesn't.
Yeah,
It's
he
not an
wrote it.
acronym.
So
It's
this
actually-
was
yeah.
this was back in the day that we didn't have digital systems. We had analog systems and chart recorders. And so it was, you know, as the telescope was looking at the sky, it's printing out on a dot matrix printer, and it's just, you know, letters and numbers, and you would see these spikes or peaks by having them run up the page. And so when the scientists got in the morning, they wrote wow, because there was something that was unique and different onto the page, and so it got called the wow signal. But over the last, you know, 40-ish years, everybody's tried to look at where do we think this is actually coming from. So which star system, which I think has been narrowed down multiple times. And over the years, number of different telescopes and stuff have looked for it and has never been reproduced. So our best assumption is that it could have been an airplane. It could have been some blip of electronics that was coming through the area. So maybe somebody was driving by with a ham radio, who knows, but it's never been reproduced.
Mark, did you study the WOW signal? Did you ever work on a dot matrix? That was a long time ago.
No, I didn't, but no, that's essentially, it usually just is, as far as I've seen, it's usually just some form of interference, or assumed to be some form of interference.
So you really have to filter out a lot. I mean, we are a noisy species, right?
Yeah.
And so is some other phenomena. How long? Okay, let's say that you've detected this. You've gone through the paces. At what point, Mark, would you be confident saying, and going to the media, going to the public, and saying it was an alien signal?
Like Sanoa said, it would be if the other telescopes that you mentioned were able to replicate or were able to observe pretty much the same thing, or at least a few of them, I would assume.
Yes.
If
And
they
then
were
you all talk? Is there like a international guideline for what happens next?
Then we go to our bosses, because then it's up to them.
They make the decision, yeah. And how can we have any idea how long or how far that signal might be traveling? We're talking just an order of magnitude. How far might it have traveled to reach our antenna?
It could be thousands of years. If the signal was strong enough, it could have
They're going to
survived.
say millions, thousands.
No, I think we're staying within our own galaxy, and I don't think we expect to see things on the more far reaches on the other side of the galactic center. So what we're looking for are things that might be under 1,000, I would say, light years at this point, based on our sensitivities.
This is very exciting. We're going to go to questions now, but really what people want to know is, when will this be up and running?
It's running. It is running.
Okay.
So
Totally, it's totally running.
It's been running all day. It's a little bit more manual. So
wait, do you mean
the
today, like it just started running today?
No. So
Oh.
it started we've been running. So in December 2021 was the first time we started taking data on the sky. And so since then, we've been off and on collecting data from the telescope itself. The electronics that I showed you in the picture, that's that computer system, the way it's set up now, was mostly installed in November. So we actually increased the amount of processing power and storage capabilities and things like that. But all along over the last year, we've been able to look at different things on the sky. We've seen pulsars, we've taken pictures of really bright galaxies, things like that. And we are still doing that. So we're still collecting the data. It's just a little bit more of a manual process. So we expect that by the next week, we should have the automated process working and functioning.
It's very exciting. So that alien signal could be coming in right now. So we don't want to extend this conversation any longer than we have to. We've got to get back. But we do have a lot of questions from people. So let's go. I'll ask you these questions from many of people watching this. And we'll try to be slightly brief in the answers just because we want to get in as many as we can. But one is, if you could compare how COSMIC will be different from how the SETI Institute, for example, used the Allen telescope array. We talked a little bit about the scale. The scale is much bigger. Are the goals actually different? I think perhaps we answered that, but Shanoa, if you could just take that and give us a sense of what the difference is.
The Allen Telescope Array is in Hat Creek Observatory in California. And that is a dedicated, it's run by the SETI Institute, but it's not fully dedicated to SETI. So there are some searches going on for ETI, but there's also pulsars, fast radio burst, galaxies. There's other work that's going on and other science work. And so they do have a program, but it's not fully dedicated to SETI. COSMIC is fully, at the moment, completely dedicated to SETI. So like I said, we can do this commensal, take a copy of the signal. And so all of those copies are completely dedicated to this search.
Mm-hmm. Mm-hmm. And if I understand this next question right, we know that the SETI Institute is, of course, involved in this. Is NASA involved in analyzing these technosignatures?
No, so our partnership is with the National Radio Astronomy Observatory, which runs the VLA, the SETI Institute, and UC Berkeley's Breakthrough Listen program.
Mm-hmm. There is a question here about the longevity of alien civilizations, and I'm going to hold off on that because I'm going to incorporate it into my final big picture question for the two of you. So we're coming back to that. Any opportunities for citizen scientists or budding citizen scientists, to get involved?
So I think eventually we're hoping to build that in. I know that Steve Croft at Berkeley was working with a summer student to try to develop another some kind of way of the public interacting with the data. But at the moment, we need to spend some time learning and understanding what the system is doing, what it's producing for data and things like that. And I think it's going to take a little bit of time before we could do a modern day version of SETI at home, because there's a lot more encryption and protections and things like that. And so there's a lot more involved than there used to be when SETI at home first launched.
And SETI at home was the background, the screensaver that was crunching the numbers, crunching the data, while people were doing other things, and that was a way that people got involved. Okay, here's one. I have to take a big breath and like loosen up for this question because this is a long one. Okay, you ready? Frank Marchis writes this one. With the current sensitivity of the combined system, at what distance could our own radio leakage be detected? From how far away do you think you could detect an eavesdropping signal? For example, such a signal equivalent to the leakage radiation from Earth today, or what kinds of eavesdropping signal strengths are you considering? Everything but an actual mathematic formula in that question. But you probably got it. You guys got that. But we could take the first bit. At what distance could our own radio leakage be detected?
I feel like really any signal could be detected like close to the observatory itself. And or something overhead, like a satellite or something like that, like an airplane or something. Yeah, so any signal, really any man-made signal close to the observatory itself, or I guess a powerful enough signal that could be detected by the array.
So usually the comparison is that in 1970s, I think it was, Arecibo sent out a signal out to space. And so everything is the comparison. This was at the maximum power. And so we compare everything to that signal. And we say, well, that's the maximum we could have produced at that time, at least. So how far away would that have to be before our telescopes could detect it? So an Arecibo-like signal could be detected out to about 9 or 10 light years is what the estimate we've come up with for COSMIC on VLA.
How far away is 9 or 10 light years? Can you help us imagine that?
Well, let's see here. Well,
compare it to your commute,
well,
to the VLA.
Well, I mean, I think our sun, the light from our sun is always 8 minutes old before it reaches us, right? So that's 8 light minutes. And so we're talking on a factor larger than that of 8 or 9 light years. And so it's quite significant. I think that if we think of 4 light years, if we needed to hear a signal from space, not that we could, but if we could, then I think it's the equivalent of 36 years for sound to travel. So it is quite a distance.
How long do you think this project will run? Someone writes, how long do you think this will run? Once this is up and going, is it have an indefinite timeline?
I think so. Hopefully indefinitely. Yeah. Yeah,
well, the VLA is planning their next generation telescope at the moment. So it's called the NG VLA for next generation VLA. And that is supposed to be quite a large instrument. And so I think that what we're hoping is that there'll be a version of COSMIC that will go into the NG VLA. But at the moment, essentially COSMIC will have the similar lifetime to whatever the VLA ends up having. But we're hoping for a minimum of 2 to 3 years.
Great. There's another question here that is about perhaps the next generation, but some of the next steps. Are there other plans to duplicate the cosmic system with in other radio astronomy telescopes, such as the CHIME telescope in Canada or ALMA in South America?
I guess those telescopes I'm not entirely sure, but for example, at Meerkat has the other project that I'm working on at Meerkat is fairly similar to COSMIC. In the sense that it is also commensal and will essentially do the same sort of signal processing, beamforming, and so on to increase survey speed.
I think otherwise there's so Meerkats in South Africa. It's part of the what they call the Pathfinder Array for the Future Square Kilometer Array, or SKA project, which is a huge global collaboration. And I think the hope is that with the system on Meerkat and a COSMIC-like system that will include also on SKA, but there's also a similar system hoping to be built on the Murchison Wide Field Array in Australia, which is a low frequency array. We're hoping to incorporate also in discussions of maybe doing something with the VLBA. So that's the Very Long Baseline Array, which has it doesn't see as much of the sky all at once, but it can see what it sees in an amazing amount of detail. So it would be a different style search.
So opportunities perhaps for some duplication. We do have to wind up at the top of the hour, and I do have a big picture question for you, but a couple other maybe we can make them brief. One is what it means to you to be searching for aliens, what it means to be trying to answer that question of, are we alone? And believe it or not, this isn't even the big picture question I have for you, but what are your thoughts about that?
I think it's an exciting challenge on top of anything else. It's a technical challenge, it's a scientific challenge, but it's also just kind of one of those questions that it's hard to look up and not try to ask, is one blue marble the only blue marble out there?
Yeah, and I would say, like, on top of it being a challenge, it's just really, it's a really good way to, it feels good to contribute specifically to something like this, in the sense that, like, whether or not, like, even if we did find something out there, or if we didn't find something out there, that's still an answer to the question, in my opinion. So yeah, so it's, yeah.
Really quickly before I ask you the big question, because I know you've been thinking about this all day, because I asked you to prepare for it. Favorite movie or book about ET or aliens, Mark?
I would say Hitchhiker's Guide to the Galaxy.
The film? The film or the book? Film. Okay.
The film. The one from the mid-2000s.
Okay. Yours?
I have a really hard time with favorites because I get into this analysis paralysis of, oh, but at this aspect and this aspect. But I think one of the recent stories that I had read, I'm much more into reading than movies, but I read the trilogy for the three-body problem, and I just loved the all-encompassing universe that the writer was able to portray regarding aliens, and everything from contact to not wanting to be contacted, and this realization that some could be friendly, some could be made friendly, and some are just not going to be nice. They're not going to show up at your door and welcome you to the neighborhood with a cake. It's going to be a lot more of a dangerous endeavor.
Okay, three-body problem and Hitchhiker's Guide. Okay, so we'll finally, to wrap this up, this big picture question has to do with time scales, and it does incorporate what one of the members of the audience asked. When we imagine making contact, I think we imagine this dialogue with the aliens, but given the timescales involved, by the time we receive it, it's quite possible that their civilization will be dead. Ditto ours if we send a message back. So what does it mean to make contact under those conditions, somewhat disappointing conditions? And what does it mean to think about these timescales beyond which even anthropologists, archaeologists think? And how does it make you think about the universe? No wrong answers. No wrong answers.
I mean, it makes you feel really small on a regular basis when you think about the fact that you might be studying a galaxy that's the light has traveled for 10 billion years, and the planet hasn't really evolved life for that long. So whenever you're thinking of astronomy, I can be very humbling. In general. But I think that one of the things that's important is one of the conversations is that not only just a signal, but something we call like a modulated signal, a signal that would actually have some form of communication or message or information. And we have all of these different cases where we've sent something out as some kind of time capsule. So even if we weren't around when another civilization discovered us, then maybe they would know something about us anyway. And so I think that's kind of one of those important things that we would love to see.
We have something similar with that as we communicate through generations. You know, we don't know our ancestors, we never talk to them, but we do learn something about them, and perhaps we hope that our children and our grandchildren will learn something about us, and that you know, that touches us. Mark, what do you think?
Yeah, I feel the same way as I did with a previous question, where to me, it's, as long as it's
to be fair, the previous question was about your favorite book, but yeah.
Yes,
okay,
yeah, previous question.
Okay.
But yeah, but it's essentially, it's just it's good knowing. It's a good thing to essentially just know that something was out there, whether or not they were like the civilization ended up dying off. Like it's just it's a way to know that, oh, that civilization might have died off, but maybe there's another one. Maybe there's another one at a different spot in the galaxy. So yeah.
And it does answer, are we alone?
Yeah, it does.
We're not alone. Well, that is the end of our discussion. Shanoa Tremblay and Mark Ruzandana, what a pleasure to talk to you. I could keep talking to you, and I hope I can at another time, but thank you so much. I really enjoyed this conversation.
Thanks for having us.
Thank you.
Well, thank you very much to all our viewers. We had 200-ish people watching us from United States, all the states, California, of course, Hawaii, Colorado, Texas, New Mexico, some people nearby you, Minnesota, Salt Lake City, some people from your family maybe has been watching you, Virginia, New York, and someone from a place called the DMV. I have no idea what this is, but it may be a far and distant planet where time is very slow.
Yes, yes.
But we also have people from elsewhere, outside United States, in Ireland. We have multiple people in Singapore, in Germany, in Japan, in Mexico, and some Canadian from Ottawa, Toronto, Vancouver Island, Yukon, etc. So thank you very much for watching us. This was a SETI talk on Cosmic. Thanks, Molly, for moderating this great moderation, I would say. I don't know if we can say it like that, but
I prefer that you do say it that way. Thank you.
Thank you.
And Shenoa and Mark for joining us virtually to tell us about this exciting project. I mean, Cosmic is going to change the way we do search for technosignature, SETI, and I'm sure we're gonna hear about it one day or another. Hopefully, it's gonna be because you get a signal. Maybe the signal is right now. Maybe right now it's in the database, and instead of processing it or checking it out, we are talking with us. So I really appreciate you took the time.
That's why the computers do all my work for me.
Okay. I'm also processing data at the same time I'm talking to you. You never know. Okay. So I just remind our viewers, the SETI Institute is a non-profit organization. We are located in the Silicon Valley in Mountain View, California. You can follow us at seti.org. Join us. The best way to support us is to join our social media platform, join our newsletters, be part of the conversation, share our videos on YouTube. These talks will be on YouTube, Instagram, Twitter, everything in the next weeks, days, I will say. So you can take the time to ask questions on those videos, and we will send them to Shenoa, Mark, and Molly, so that we'll take the time to answer to them. So thank you very much for watching us again. You can also make a donation. You just go to seti.org, you click on this right button called donate. And if you want to support the search, if you want to be part of the search, you can give us a few dollars, a few $100,000. We built our own antenna, a new instrument to search for more life elsewhere in a galaxy. And I will just finish by saying that it's finally getting clear in California after like weeks of rain. So if you are in California or if you are elsewhere and it's dark right now, look up. Maybe somewhere in the sky there is a star over there, and maybe around this star there is a planet, and around this planet there is a civilization doing a SETI talk about an instrument that they will use to detect some intelligent civilization. Maybe they will detect us. So say hi to them. Thank you again. Bye-bye.